Hello everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. In today's video we're going to be looking at the circle and trying to get at this ephemeral notion of the area of part of a circle along the lines of Archimedes' thinking of looking at inscribed and circumscribed polygonal approximations. Along the way we're going to introduce a very important notion called the half slope, which will figure prominently in our further investigations of applications of calculus. So the starting point is our unit circle in the plane with this familiar, I hope, rational parametrization. That e of t is 1 minus t squared over 1 plus t squared, comma 2t over 1 plus t squared. And geometrically, it means we look at the point on the y-coordinate with coordinate t, connect that to the point minus 1, 0 here, and wherever it meets the circle in the other place, that's the point E of t. Okay, so here are 2 points on the circle. E of a quarter, which you can calculate as 15 over 17 and 8 over 17, that's the point A. And E of 2/3, which is 5/13 and 12/13, which is the point B. And naturally enough, you can sort of see Pythagorean triples here. There's the triple 8, 15, 17, and 5, 12, 13, sort of behind the scenes here. Okay, so here are 2 points on the circle, exact, precise, rational points. And here we have the tangents at A and B. And we're going to be interested in the meat of these tangents. Let's denote that by C. All right, so now then in terms of this geometry here, we're going to define 2 quantities. Let's call them G and H. G is going to be an inscribed polygonal path, or its signed area. The signed area of the side AB, the oriented edge AB. In other words, that's the oriented little triangle there, OAB. And H will be the signed area of the spline ACB. That's ACB. So that's that bigger quadrilateral area that's containing this arc. So the arc actually that the circle forms between A and B is what maybe we're interested in. We're interested, does this have an area? And that's actually quite problematic. But what we can do is we can look for something inside, which is the G, the signed area of this triangular piece, and something outside, which is the H, which is the signed area of this quadrilateral piece obtained by looking at the tangents. All right, so to get specific, let's have a look at what actually happens on the unit circle. We're going to take 2 points, A and B. A is E of t, so it has that familiar rational parametrized form, and B is E of u, so a similar form with parameter u. So these are 2 points on the unit circle. Now, we want to calculate, first of all, the secant, AB, the chord joining them, and we know how to do that. We can use projective coordinates. We can convert each of these to projective coordinates and use our join of points formula. And we get AB is the line minus 1 plus tu to 1 minus tu to t plus u. So that's the chord or the secant joining 2 points with parameters t and u on the unit circle. Now to get a tangent, we simply set t equals u. That will give us the tangent at the point A, E of t. So when t is u, this term here becomes minus 1 plus t squared. Here we get 1 minus t squared, and here we get 2t. So that's the equation of the tangent to the curve at A. And if we want to write a more familiar equation, we write this plus 1 minus t squared x plus 2ty equals 0. We can bring the constant term to the other side, then it would become 1 minus t squared times x plus 2ty equals 1 plus t squared. But it's a little bit maybe more natural to divide by that right-hand side. So then we get the equation 1 minus t squared over 1 plus t squared times x plus 2t over 1 plus t squared times y equals 1. And that's very nice because we see that the coefficients of x and y are exactly the x and y coordinates of the point A at which we're creating a tangent. So we can summarize that here. There's the unit circle. There's the point A on it with coordinates RS. Okay. Then what is the equation of that tangent line? Well, it's r times x plus s times y equals 1. Or if we wanted to write it out, everything on one side, it would be the equation minus 1 plus rx plus sy equals 0. So if A is the point rs on x squared plus y squared equals 1. It's a very important formula that allows us very quickly to write down the equation of a tangent line to a point on the unit circle. So now that we're in possession of the tangent lines to the unit circle, we can go one step further and obtain the meet of two tangent lines. So in the diagram here, A and B are points on the circle, tangent line at A, tangent line at B. Those two tangent lines are going to meet at some external point C. And it's very nice to have a formula for C in terms of the parameters of A and B. It's especially useful when we're interested in circumscribing polygons to the circle. All right, so let's suppose that we have points E of t and E of u on the unit circle, just as before. And these are the formulas for the tangent lines at these 2 points that we've just derived. And then we can find where these meet. The meet of lines formula, we take that and calculate this triple. This is then the projective coordinates of the meet of these two lines. And it turns out to be the point 2 times u minus t, 1 plus tu, and then to 2u minus t, 1 minus tu, to 2u minus t, t plus u. And again, we have a common factor. Well, there's a common factor of 2, but also of u minus t. And since we're supposing that u and t are not actually the same, we have two distinct points, we can divide by the 2 and the u minus t to get the simpler expression for the point C. 1 plus tu to 1 minus tu to t plus u. And I remind you that to go to the affine, more familiar coordinates, we just divide by this first term. So the x-coordinate is actually 1 minus tu over 1 plus tu, and the y-coordinate is t plus u over 1 plus tu. Now have a look at this. It's a very interesting formula here. So this is very much like the rational parametrization of a single point. If the parameter was t, we would have 1 minus t squared over 1 plus t squared, and we would have 2t over 1 plus t squared. Sort of what's happening in that formula is that the t is sort of being broken up. So instead of having t squared, we have t times u. Instead of having 2t, we have t plus u. So that's a kind of a nice way of remembering it. Okay, and here's specifically what actually happens to show you that you can calculate everything here completely explicitly and concretely. So if A is, say, e of 1/4, so that would be the point that you get by joining here to the point on the y-axis with coordinate 1/4, okay? Then that turns out to be the point 15 over 17, 8 over 17. So there's a Pythagorean triple involved implicitly there. The Pythagorean triple 8, 15, and 17. That's the coordinates of A. And B, let's say, is e of 2/3. So what you get when you go up 2/3 here and join up, that's the point 5/13, 12/13, of course associated to the triple 5, 12, 13. Okay, then you can easily plug these values, 1/4 and 2/3, into here, and either in projective coordinates or in affine coordinates. In projective coordinates, you end up getting 7 over 6, 5 over 6, and 11 over 12 as the entries there. And because they're projective coordinates, we can scale to get rid of the fractions. We can multiply through by 12 to give us 14 to 10 to 11. One of the advantages in using projective coordinates. And then if we want to convert it to affine coordinates, we divide by the first term, giving us 10 over 14, or 5 over 7, and 11 over 14 as the y-coordinate. And I'm showing you also the equations of the tangents here. The tangent to A, since A is 15 over 17 and 8 over 17, the tangent line is just 15 over 17 times x plus 8 over 17 times y equals 1, multiplying through by 17, 15x plus 8y equals 17. And similarly, b, the tangent line is 5x plus 12y equals 13. All right, so now let's write down the inscribed signed area. If we have 2 points A and B on the circle, they cut out a circular arc, we might be interested in the approximate area of that arc. Maybe we don't know if it actually has an exact area, but we would like to get some kind of approximation. So one idea is just to take the linear approximation where you just cut off with this chord AB. In other words, we're just taking the signed area of the side AB. Well, if A and B are E of t and E of u respectively, then we know what these vectors are, and we can just use the formula for the signed area of a basic triangle. So we're just going to take the cross product of the vector 1 minus t squared over 1 plus t squared, 2t over 1 plus t squared, with the corresponding one over here, 1 minus u squared over 1 plus u squared, 2u over 1 plus u squared. And I remind you that that's this quantity times this quantity minus this times this. And there's a half. So when we get a common denominator, we get this expression here. You can check that this simplifies to u minus t plus u squared t minus t squared u, all over the factors 1 plus t squared, 1 plus u squared. And then this has a common factor of u minus t, which is not surprising. The other factor is 1 plus tu. So altogether, the formula for the signed area of this little triangle formed by these 2 points on the unit circle is u minus t times 1 plus tu over 1 plus t squared times 1 plus u squared. All in terms of the parameters t and u that denote the points A and B, that specify the points we're talking about. All right, so following Archimedes, we now have a sort of an inscribed polygonal approximation to this circular arc that we're interested in. And now we're going to find a circumscribed approximation as well, sort of capturing what we're interested in between 2 things that we have control over. So it appears to be a little bit more complicated, but surprisingly the answer turns out to be simpler. So we're looking at the points A and B just as before, and now we have this additional point C where the 2 tangents meet. And so now we're going to consider this quadrilateral ACBO, or in terms of splines, we're going to look at H, which is the signed area of ACB, the spline ACB. All right. Well, according to the definition of the signed area of a spline, it's the signed area of AC plus the signed area of CB. And each of those are things that we know because we know the coordinates of these points, so we know what these vectors are. We're going to just be taking cross products of vectors. So the signed area of AC will be 1/2 of, here is the vector OA, and here is the vector OC. It's essentially the point C that we calculated in the previous slide. Plus then a corresponding term for CB from here to here, where we take the cross product of the vector OC down here with the vector OB. So you can do both of these calculations. And it turns out, not surprisingly, that they're both the same. So the value of this first one equals the value of the second one. And they're both equal to 1/2 of u minus t over 1 plus tu. So we get 2 such terms, and when we add them together, the halves disappear, and we just get u minus t over 1 plus tu. So if we go back to our motivating example, our points A and B, which are E of 1/4 and E of 2/3, and I remind you the point C that we got was 5/7 and 11/14, then we can now ask, well, what is the approximate area, in quotes, of this circular arc OAB? So the portion of the circle cut out by these 2 rays from the origin to A and from origin to B. Well, that area is a tentative quantity. It's ephemeral. It's not something that we can get our hands directly on, as Archimedes already probably had an intuition for, and really as substantiated by so many dozens of people who have tried to calculate circular areas. No one is able to actually get a hold of the thing exactly. And that's the situation that's intrinsically, part of the story. It's just not something that we can get at exactly. But we can get at bounds. We can talk about intervals. We can say, whatever it is, it's inside here. And the technology that we've just introduced allows us exactly to do that. So we now have a lower bound and an upper bound. The lower bound is what you get when you take this quantity g. It's the signed area of the triangle OAB. So we just perform that cut there along the line, and that triangle will be some lower bound for it. And we know what the signed area of that is. It's u minus t times 1 plus tu over 1 plus t squared, 1 plus u squared. And when t and u are 1/4 and 2/3, you can plug in and you get 70 over 221. Correspondingly, an upper bound will be this quadrilateral area, the circumscribed spline. That's the signed area of OACB, that quadrilateral, or in terms of just splines, the signed area of the spline ACB. We're calling that H. And the formula for that in general was u minus t over 1 plus tu. For these particular values, we're going to get 5 over 14. So we can now say that the approximate area, or maybe the approx area of this circular arc is, well, we can't say it's exactly a number, but we can at least ascribe a certain interval to it. The interval between our lower bound, which is 70 over 221, and this upper bound, which is 5/14. And that's really what the calculus allows us to do, is to find these bounds for certain things. Some things we can get at exactly. Other things we can only get at approximately, and we have to acknowledge that. That's what we're doing here. We're acknowledging that and saying, okay, there's an interval. And that's all that there is. There's only intervals. There may be our more refined intervals, sure, but there's never actually a single absolute exact value. Only ever intervals. It's just the way it is. Now I really want to elucidate the gap that we have here between what we're doing here and the conventional approach that you find in most calculus courses. There's a separation here. We're going down a different road. And I really want to promote the idea that the road that we're going down is a better road than the traditional one. It's not a case of, there's two roads and you can choose either one. It's a case of this road actually makes logical exact sense and this one doesn't. Okay, so let me try to get a little bit of that across. So here is a brief overview of the modern angular approach to the same question. The same 2 points, here's A, here's B, and we're interested in this area of this circular arc. Okay, so in modern treatments, the question of what this area is and the question of what this angle is are very, very closely connected. So the usual story is that the area of the circular arc, OAB, is half of the angle. Let's call the angle theta, okay, in quotes. And the reason that there's a half there is because, well, if you look at the entire angle, the way we measure angles is through these radians, and there's altogether 2 pi all the way around. But the corresponding area of the circle is pi. Okay, so if 2 pi radians correspond to an area of pi, then angle of theta should correspond to an area of theta over 2. Okay, so how do we get at the angle then? Well, in standard treatments, what you do is you invoke some so-called inverse circular functions. This is the sort of standard fashion. You could take these two vectors, say the vector v, which is 15/17 and 8/17, and the vector u, which is 5/13 and 12/13. Fair enough. And then we can invoke this formula, in quotes, that tells us that the cosine of this angle is v dot u over the length of v times the length of u. Now in this case, these two vectors are both unit vectors because they're on the circle. So this actually simplifies. There's often, in general, there's complications with the denominator here, but in this case there aren't. So we're just talking about v dot u, which is the dot product of these two vectors. Basically this times this plus this times this. And that turns out to be 171 over 221. So that's not problematic at all. But now the problem is how to unravel this to get at the theta itself. And in order to do that, we have to invoke this arc cosine or inverse cosine function. So theta is then arc cosine of 171 over 221. And now students will just know how to press the appropriate button on a calculator, but actually the official formula is something like this. That if we replace the 171 over 221 with, say, z, then the formula is something like this. Pi over 2 minus z minus a half z cubed over 3 minus 1 times 3 over 2 times 4 times z to the 5th over 5 minus 1 times 3 times 5 over 2 times 4 times 6 times z to the 7th over 7. And hopefully by this time you're kind of getting the pattern here. You can guess what the next one would be a z to the 9th over 9, and there would be a 1 times 3 times 5 times 7 over 2 times 4 times 6 times 8. Okay, so we know what the pattern is. And that's what we're supposed to do. We're supposed to carry on subtracting terms like this forever and ever. Okay, and at the end of the forever and ever, lo and behold, we have the angle theta. Now, as I hope you all have at least some sympathy with here, this is just not valid arithmetic. It's not a question of opinion or, or taste. It's just, this is just not valid arithmetic. We are not in a position to do an infinite number of arithmetical operations as this formula really is demanding us to do. It's saying, do the following infinite number of things. And by the time you've done the infinite number of things, then you will have the angle theta between these two vectors. Well, I'm sorry, ladies and gentlemen, there just is no angle theta between those two vectors. This is not a proper formula. It's not valid arithmetic. It's not something that we can do. It's only something that we can wave our hands in the direction of and sort of rely on our calculator spitting out 10 or 20 decimal places saying, see, we're getting something close to what we want, something that exists out there at the edge of the universe, on the other side of the universe. Okay, so this is the standard story that undergraduates just learn to absorb. They just play along, say, okay, if that's what we have to do, that's what we have to do. But in this course, we're not doing that, okay? We are not allowing this kind of infinite arithmetic, which is not valid. We're not pretending that it's a legitimate kind of thing to do. So this is just simply wrong mathematics at the level of pure mathematics. Even though finite truncations might be very useful, in fact, are very useful. I have no problem with truncating this and making some finite computation and saying, here's something that an applied mathematician can use. Great. But the claim that you can talk about an infinite thing, no, we're not going to do that. Now, the implications of abandoning the angular approach are very significant for us. It means that many of the techniques that are standard in the current treatment of calculus, where you invoke angles and then you describe certain things in terms of angles, we're going to have to circumvent that. We're going to have to find replacements for that way of thinking. And fortunately, what we've done today already sets a very good foundation for that. We're going to see that the half slopes h that we're talking about are very powerful replacement for angles and turn out to be superior to angles in most applications having to do with calculus, dynamics, kinematics, and geometry. So let's clarify what we're talking about here. Suppose that we have two vectors, v and u, on the unit circle, okay, given by points A and B, which as usual are E of t and E of u. We have our meet of tangents, point C. We have this quadrilateral here formed by the origin, the point A, C, and B. And we've defined h to be the signed area of this thing. In other words, the signed area of the spline ACB. And we've seen that in terms of t and u, this is u minus t over 1 plus tu, a very elegant formula. So we're going to give this a name. We're going to now call this the half slope between the vectors v and u. This is some kind of replacement for an angle or an area. Okay? It's some kind of replacement for an area or an angle. And so what we're going to do is we're going to denote it on the diagram by a little straight line with an arrow. That'll be h there. And I'm just going to initially observe two things about this. That in the special case when t is 0, in other words, when the point A is e of 0, which is actually the point 1, 0. So if this point was just there, then the formula reduces. If t is 0, we just get u. In other words, the half slope then is just the same as the parameter u for the second point. This gives us a geometrical interpretation, or an interpretation of what this parameter u actually denotes. Another way of thinking about it is it's the area, the signed area of the quadrilateral formed by the point 1, 0 and whatever point we're interested in. Another very interesting aspect is the other quantity g that we've talked about, which is the inscribed thing. I remind you that's just what you get when you join A and B with the chord and look at that smaller inscribed triangle. It turns out that g is equal to h over 1 plus h squared. So the inscribed area is actually determined by the circumscribed area. If you know this quantity, then you know the g quantity through this secondary relation, which is pleasant to establish. So these are just some clues that this quantity h, this half slope, is potentially a useful device, and we are going to see this further on as we move into the course and eventually into geometrical applications of the calculus. The half slope is going to be a good alternative to thinking about angles for a lot of things in the algebraic calculus. So there's much to learn. I'm Norman Weilberger. Thanks for listening.